we just call the tokens is just ironic because it is a unit of value. So like what we've done is immediately turn all of the digital communications into a commodity. So like that's stage 4, and like, yeah, I don't know what stage 4 is, but like that's like we do a NASDAQ, you know what I mean? Or like Quant integrates with us to create the first like crypto / traditional exchange. And then we will petition to create a digital commodities class and be the ones who made crypto mainstream.
But our whole thing is to not show that that we know how to attribute value to a certain piece of data, but to provide the rails by which to exchange data.
Exactly. That's exactly it. And that's where like the role of DAG comes in, because that's how these machine-to-machine communications make payments. And it removes the middleman, and it allows for the whole system's cryptographic security to work seamlessly. So that's the aha moment.
And autonomously.
Autonomously, exactly. Yeah. So the thing is here, like, I'll give you the ending. This is going to be a Shakespearean talk, where the ending is individuals. There will be two types of developers who use us. There will be app developers like data scientists and data engineers who want to just build a secure pipeline. And there'll be other engineers who are interested in the infrastructure side of it and contributing to the open source stuff and creating integrations with like Spark or whatever and all those kinds of things. Okay. So like people who use the integrations or people who make them.
Over the course of the next couple of weeks, we're going to start shifting our marketing materials and things that put DAG at the center, because that's our success, and then building off of that, right?
Yep.
Like we don't need an infinitely scalable architecture to do peer-to-peer network. We knew that all along. All these slight nuances that build us up from a point of confidence versus leading with a point that we don't have sources of data that are cryptographically secure.
So the idea here is that the distributed ledger was just a simple data type that we used as a proof of example of the consensus architecture to show that, hey, this will actually scale. And so if blockchain has value or like big data has value, then you can guarantee that this does. Okay, great. From the perspective of a type 2 developer, a infrastructure tools guy who works at Mongo or works on Spark at Databricks, whatever, from their perspective, what they will be doing is instead of writing smart contracts for Ethereum, they will be creating connector pieces for specific data types and specific interfaces. So like for us right now, our answer was what we did for our architecture is that we've created a simple validation like logic or scheme for the data structure of a linked list. Why did we choose linked list, especially for our DAG token? The reason why is because a linked list as a representation of an account's information carries topological order such that we don't have to worry about nodes disagreeing about things being received at certain times. It's an unsolved problem in distributed systems because time doesn't exist. It's really all relative. And so like events occur within what we call I'm forgetting the specific term. We don't need to go this deep, but basically like concurrent processes require a fundamental data type on which to operate from a mathematical sense when we're trying to understand, steady states of dynamical systems, okay? And so the reason why what we did was we said, hey, okay, we have data passing through the network and we want to solve this consensus problem, right? So what we realized was that specifically, like what we do is we process transactions that are linked lists, and then we process blocks that are what's called a graph, like a directed acyclic graph, and we form that graph. So those two data structures that we form are the key building blocks upon which more complex data can be created. And the way that this all works is that a transaction, which is a linked list, is actually, from like our perspective of validating data, it is essentially the same like type class-ish as a checkpoint block. But what we did was we showed that we can create this hypergraph structure out of a linked list. Now, fast forward, we have people who want to validate lots of even more complex data. All complex data is a graph. Anything else is something that's similar to a linked list. The reason why is because linked list, linear structure, graph, nonlinear structure, okay? All data structures can be formulated into those two different pots without getting into specifics. That's hand-wavedly correct. So The idea here is that while we have created a fundamental architecture using primitive data types of a linked list and a graph, users who are building plugins to their kinds of tools, or perhaps even if there's a custom component to their app and they're the first type of developer, these users will be defining their own custom data types the same way we define the data types of Scala primitives, like a graph or like a linked list. We just took a language, Scala, and we took the implementation of this thing, and we created a logic around validating the implementation of this type of a data structure. Individual users, on the other hand, can create their own data structures that fit within this model. And that's where things start to get kind of, fun. So the answer here, not really answer, but the explanation is that, actually, here's what I want to do. Here's how I'm going to tie this off. This is going to make sense. I'm going to explain to you how Ethereum works, and I'm going to then sort of parallel that to Constellation, okay? Ethereum is sort of like, what Ethereum does is that it created something called a VM, which can, perform actions within some kind of a sandboxed environment. A VM being a virtual computer, something that's shared across nodes, so it's a stateful, basically like set of disk that can then be operated on in memory and then sequentially sort of executed, whatever. We know how smart contracts work. But under the hood, the actual mathematical logic and the reason why we know they work is because of our ability to use formal verification. Now, formal verification is the quintessential homomorphic encryption, sure, that's part of blockchain tech. But verification, on the other hand, is how we're able to build resilient distributed systems. So Ethereum uses these things called opcodes, and there are two types of languages. One called dynamic and one called static. Dynamic are things like Python, JavaScript, stuff that I don't like for many reasons. And what they do is they use something called an interpreter. Now, an interpreter takes what's something called an opcode, or which is not actually bytecode that a computer knows how to register. It's a small, low-level program written in a statically typed language that then interprets the information that pipes into it. Now, you can do some cool stuff simply with it, but that's like a mode of computing. Now, the Ethereum people have absolutely no fucking idea how to build a distributed system. Like, all those kids didn't have degrees. They didn't have any idea how even the most basic fucking scalable architecture works. So what they did, like a bunch of, naive college kids who wouldn't listen to fucking direction, is that they repeated a bunch of issues from 10 years ago with the monolithic architecture, and they used a dynamically typed language. But they used this notion of opcodes and dynamic languages in order to verify the state of their network. It makes sense for someone who only knows Ruby on Rails and JavaScript, and they just fundamentally don't know how these systems work under the hood. But it's just comically laughable that we could somehow think that a sandbox that can verify JSON objects with 4 types that don't have any kind of modifiers can do anything that's worth of any value. So let's just backtrack right here without talking too much shit. What we have done, and this is what blockchain cohomology does, is that we have created a framework for formal verification in such a way that we are able to verify the state of a distributed system using only types. Let that sink in. We have rewritten how formal verification works for decentralized applications using type theory. That's the paper I got published. So fundamentally, what we did is we showed, hey, the way we use these types, the way we use these static languages and ways of understanding different, data formats, whatever, the way that we do that in a scalable environment, we know that it's compatible with verifying the state of a blockchain network, which is a type of a distributed system that's stateful. And so that's the magic. Basically, instead of people writing smart contracts, you will define your own user-defined data type or something similar to that. Like, for instance, if I just wanted to, for Magic, for instance, Biggles, if we wanted to just create an app, right? Just like a Twitter clone, and maybe a Twitter clone where you can vote or share evidence about facts about shit, right? We literally would only need the linked list data structure. See what I mean? It'd be very simple. We could extend that, add a little extra logic, great. But if you want to deal with Spark's shuffle RDD format, we then build an add-on within it in order to process that data type And thus Spark's whole set of data types and their shit is now available for app developers who don't need to know how Spark works. They can just import and assume it's working correctly. So that's kind of like how these things are all going to play out. And so like, yeah, the concept of a smart contract isn't going to exist in 10 years because of this. So yeah.
When you say type theory, is that the same as a type class?
Yes, sir. And the reason why is because of something called the Curry-Howard correspondence. When I use functional programming, you see what I mean? MapReduce, the type of stuff all of our data engineers use. There is a one-to-one mathematical relationship from the actual pure function itself to an equation. So what I can do is implement my code within it's called a sufficient type system. And then I know that up to the sufficiency of my type system, which is, you can just think of it as like the number of rungs on a ladder. You can add as many as you want. For Scala, it's like 22,000 or something. It's absurd. We're fine. And so basically within that framework, I know that my code, if it checks out at compile time because of these mathematical laws that we know are baked into the class itself, you can guarantee that things are factual.
Thanks.
That is amazing. I think we should cut that section out and post it and be like, quote you with an article saying smart contracts don't exist in 10 years anymore.
Yeah, it's a fucking joke. Like, if you're still building dApps, just like get a new job or start looking at DAGs.
So great. So this is actually a really good point. So in what you just said, let's backtrack and go.
Yep.
Relate that to how we created DAG, the currency, on our network and are cryptographically securing a simple data structure such as a ledger balance and creating an ecosystem that works within those parameters, and how we're going to evolve to phase 2, which is cryptographically securing complex data structures and how that will work.
Totally. So basically what happens is that a user defines their own complex data structure, right? And they can define a data structure without telling you guys the specifics of all the data structures, okay? There are data structures form a hierarchy, okay? So you can bifurcate them like forming a tree. So imagine I'm walking down like one of those, what is the thing where you put a ball and then it goes down and eventually ends up in a hole? You know what I mean?
Plinko.
It's called a plinko.
Oh. Okay, cool. Well, anyway, we bifurcate basically from linear to nonlinear data structures. And Constellation forms one, a parent linear type and a parent complex graph, hypergraph type. Using non-math words. By creating the linked list in the graph, we have given like the data structure primitive, like the primitive, we'll call it, the parent type or the primitive. There are two ways of describing the same things: parent type looking top down, primitive looking bottom up. And so what we do is we have implemented and verified the accuracy of primitives such that more complex data based upon these primitives can be formed. These primitives that we have verified are custom case classes, but they are implementations of, you can think of one, a linked list, which is a topological blah, 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 whatever data structure, and then a graph, which does whatever. So that is the building blocks upon which a person will then say, hey, I care about data that has multiple events happening at the same time. I use a graph. Oh, I have data that cares about the linear order or thing of a stream of data coming through. I use a linked list. I have a database update. I literally just use a user-defined data type like a schema, and it doesn't matter. So these are the simple points. Actually, yes. Think about it in your head this way, guys. There are 3 types of state channels. 3 types of state channels correspond to like dimensions, like a dot, a line, and a square, okay? Like we're getting back into flatland here, okay? Now a dot is the kind of atomic upsert state channel, that kind of a data structure where it's literally, we just want to send a transaction and make sure the response is good. So what we do is we create a cycle within an actual linked list, and that is sort of like a 0th dimension like piece of data. We have a first order piece of data, dimension order, which is a line, which is like a linked list. This gives us order. We have a second order dimension of complexity, which is a graph, which tells us about concurrent behavior. And so, yeah, and if you guys, I won't go into it here, but if you want to understand why hypergraph, that's like another layer of complexity on top. I don't need to get there, but the end result here is that from these primitive data structures, because of how I built them, the sum total of the network is what's called a hypergraph. You can also make a linked list out of, instead of the items in the linked list being a first order dot, transaction, right? You can make a dot one dimensional object thing as a graph that's 2D. So that's how that becomes a hypergraph. You like nest these things inside of each other so that you create this sort of natural platform out of optimized network topologies, which the actual internet is how that works. So we sort of tried to model the incentives there using something. There's also onion routing, and then HTTP is very similar to that and how it recursively traverses stuff across nodes. So that is exactly what we do, how we're different, and sort of like the narrative is we created the primitive data types upon which complex data types can be built. You can build by using the special monadic interface that we did, we can also build, various, user-defined data types out of either a unit, a linked list, or a graph, out of other lists, linked lists, or graphs. And these user-defined data types stack on each other so that the layer validates, the levels of the network validate each layer in tandem. And so that's the commensurate kind of final behavior. But the goal here is this. Instead of Ethereum, we created a new type of formal verification using raw type theory and a vetted type system, the Scala type system. By creating these primitives, we have given people the building blocks upon which any complex data structure can be built. These complex data structures can thus then again become the primitives to even more complex data structures. That is how we become a hypergraph. Finn.
Love it. Now boil this down to the simplest terms on how that relates to the creation of DAG and using primitives to create DAG and cryptographically securing ledger balances that will evolve into complex data structures.
Got it. So the answer here is this. What was the evolution of DAG? We didn't create verification for ledger balances. We created verification for data types such that users could verify and validate increasingly complex data. We basically flipped the original verification mode of smart contracts on its head by allowing the nodes themselves with a reputation attached to create their own meta lineage history such that it can reason on its own in the same way that a centralized Ethereum supercomputer is. Because we should just call Ethereum a centralized autonomous execution platform because it's centralized. But we are a decentralized autonomous execution platform. Remember, like the original title actually for Constellation was like a microservices architecture. So that's exactly what this is. So instead of smart contracts all living together, we distribute it. And that's it.
So Wyatt, in another way, could you say that the DAG is basically just a very simple, basically the simplest data type that you can come up with in the network, and thus, however, the network is engineered in such a way that it can handle all these other more complex data types and data types of data types.
Exactly.
But the MVP is we show the most simple data type possible, which has the result of verifying a ledger balance. But in essence, it is actually a data type that we're showing as an MVP.
Exactly. That is exactly it. We just took the simplest thing and we knew that the simplest MVP was good enough to build distributed ledger and our own currency and our own network. So that's why we did it. And now we basically have this whole thing done, vetted. We have extra money and we have the infrastructure in place for machine communication already. So these complex data sets, like in phase 2, that's actually what I was working on today. I mean, I'm still finishing out the interface for it. So it's ironic we're talking about this, but yeah, we'll be able to do a demo demonstrating this sooner than later, just to at least show it. And then basically like the last part after this, which is that machine-to-machine thing, is basically just like, okay, you've shown that complex data now works, which is great. We can do that in like a unit test. Then all we need to do is design the architecture for phase 3. Yeah, so that's phase 3, which is now knowing that the complex data works. Can we build hardware, okay, like actual, like, specific custom sensors that can, give us like basically real-time, like consensus at the source in the field, verification. Like everything is user-based right now. And in phase 2, it's like, do I have a password? It's all about data. Part 3 is about verifying the physical systems themselves. So if we know the data is accurate and the data is coming from the system is accurate, then we know that our view of the system is accurate because we're just reading the data too. Sorry, Douglas, go ahead.
Oh, no, yeah, I'm the one that's cutting people off here. So could we partner, or do you not believe that there's anybody doing this at the level of fidelity that you require?
Oh, I think that we totally could partner. And also, I'm not an expert in hardware. So I could do some research on, the most I actually know about hardware is what I've learned from building Constellation and getting into crypto. So I'm actually notoriously bad at circuits and shit like that and building ASICs. That's not my forte. So what we want to do is find outfits that are creating something similar to what's called a one-time pad, or devices that use more complex verification, or sorry, what I'd say, verification or authentication schemes. I can't remember which one it is for these. I'll find them. Basically, there's more complex ways of creating these ASIC chips, and all we need to do is just find someone. And I think for phase 3, if we just have it planned out, and we're like, hey, what do you guys use for this? Then we can just use their shit. Or we can just say, hey, here's an external vendor who we want to build this ASIC chip. And assuming the ASIC is totally fine, then great. So I can give them enough specs to tell them what it needs to be like, and then to verify that tests work on the network. But like, I'm not going to be doing any hardware engineering, man.
No, and I don't want to get into hardware business. The saying is they call it hardware because it's hard. Find somebody else to deal with it.
But that's, that should be, comparably easy to farm that out. Even Coffeetalk has like manufacturers where he can spec out chips and stuff like that. So if we have specs, he could roll that by them, and even if they can't produce it, they'll connect us to people or companies who can do that stuff.
Exactly. We also have years to figure this out. So, we'll figure it out by next year.
The hardware stuff is super impressive, but that's a big vision,
Yeah, exactly. And a lot of people have tried to verify remote code execution. Like the original guys who did Ripple actually tried this, and then they ended up building Corda, which they dropped. And then they tried to solve it with something similar to like the solution that we have by creating a type system in a VM. But I don't think there was any more traction for that, like beyond any, simple Ethereum type, shit.
Yeah.
So the thing I'm trying to basically say here is there is an unsolved problem of remote code verification. We provide tools to solve that. There may be something I don't know about in like network engineering or on hardware that means that, I don't know, in their system that our solution might not be great. And the reason I say that is just because I don't know what I don't know. So the only thing here is not like, we're not going to get gotcha'd like, oh, our shit just fundamentally doesn't work. It's going to be like, oh, well, where does it break down? And right now I can guarantee you like DAG, hypergraph network, totally fine. But when we move into building custom solutions for like the fucking Air Force with like drones and shit, like I'm going to have to go into research mode the same way I did when I founded Constellation.
Yeah, what about that Grigore's runtime verification tool? Am I missing the mark on that one?
Oh, so our stuff is way beyond his bullshit.
Okay.
So I'm actually going to, I'm not kidding. So I found a different research group out of Amsterdam that is a crypto group, which puts his research to shame. He's basically just getting money from other people to get a stamp of approval for shit, because what he does is he builds a model inside of a sandbox environment and then says the algorithm is correct. His code could be wrong, the implementation could be wrong, it's totally fucked. What's really cool, however, is that the blockchain people in the Netherlands, who are dope, called Statebox, is that they created a way to verify at compile time, not even just like runtime complexity, but compile time, verify the stability, or rather the accuracy of your model and your code, in the same way that like what he does is that he adds extra stuff to the process and then retroactively tries to prove it in the limit in the future. Like that's cool, and that definitely needs to exist for like Ethereum type systems. But what we've done is fundamentally, we have shown that Ethereum's limitations are not limitations. We can do them, we did. Like everything that they said we will never be able to do in ETH, we did. So by just using raw homotopy type theory, just pure mathematicians, not even computer scientists, we're able to verify that stuff. And the guys at Statebox all use the same mathematical model that I used for building our primitives. So it's really cool that like once I'm done with the state channels, I can try to plug in their tool or maybe like help build a Scala one or something with the type system in order to just show, hey, at every single given build based upon this proof thing that we have for the type system, you can read out the actual fucking proof, which is dope. There are systems like Coke, which is what Grigori was doing just to like, sell, service to somebody, where they prove theorems for you. And that relies on the Curry-Howard correspondence that I mentioned earlier. And that's basically just what we did. I said, hey, you're theorem proving using Curry-Howard, functional programming uses Curry-Howard, why don't we just do them all at the same time? And voila, we created truly like concurrent autonomous systems.
We met a dude at Decode that has a verification code quality verification platform. I may be way out of line, but it seems pretty novel and interesting. It's worth at least having a conversation with him and seeing what he's up to. He would give us access to his platform for free just to test shit out. But if there was a way to weave it into stuff in the future, but that stuff doesn't matter right now. Not to discredit your vision by any nth degree, but going back to the data pipelines and the software layer, like, dude, there's so much money and action to be had right there.
Oh, yeah, absolutely. I mean, yeah, dude, phase 3 can take 2021. Once we've got our shit, we can embark on another crazy adventure.
And I can give him a shot because I agree. I've seen this. He has something a little different. I think that's why.
Okay, cool.
Yeah, and he's a really fucking good guy. He's the type of guy you'd want to drink beers with. So.
Okay.
Yeah, Ben.
I'm good. Yeah, line it up and I'll be there.
Okay, I'm hitting my wall here in terms of timing. What I was really hoping to dive into, and I guess we'll have to do it next time, was talking about making sure that we understand the role of compressed files and kind of referencing those compressed files, and something that we talked about earlier today. And I'd like to save that till next week for time, but I think this episode is actually spot on.
Well, I can just answer really quickly for the transcription so we can start somewhere. The answer to your first question, which is where does homomorphic or compression fall in, is that part of our scalable solution is that we help users with data types create uniquely identifiable like pointers or objects or units of data that reference it. So that's it. You're just reducing the size of the data you want to put in your database the same way that you compress files the same way when you download an app, all those files are compressed. So is
Constellation just another, are we just building something that creates another referential database?
Well, yeah, I mean, the end of the day is that the data itself is what would go into a referential database, but you can run jobs on it, you can stream it, you can do anything on this stuff. So it's just more versatile.
Great. This is great stuff, Wyatt. This is really fun, man. This is fun. We're now finally making space for it, and it makes sense to start doing this again and getting into a habit and getting us all fucking next level.
Yeah, dude, I'm stoked, man. It all makes sense by the end of the year, like everything. You know what I mean? Like there will be no ambiguities.
Great. Thanks for the time, man. I love this stuff. All right. All right. So I gotta jump, guys. This is awesome, Wyatt. You are on point. This is great.
Oh, thanks, man.
All right, guys.
All right, thank you, guys. Talk to you soon.
You guys.
Later.